Alright, we're going to combine these last two pages into one because we're really not going to extend too far into Green's theorem today when we're talking about when we're talking about curl and divergence. But there's just like a little extension. So theorem 11, if F is equal to Pi plus Qj plus Rk is, say, okay, we have a vector field in on R3, and P, Q, and R have continuous second order partial derivatives, then the divergence of the curl of F is equal to 0. Remember, the curl of F is going to give us a vector, and then the divergence is going to be the dot product, all right? And so the divergence of curl of F is just going to be 0. Here's the proof where we just are taking the gradient of our curl of F, and again, this curl of F equation just comes from the beginning at the top. Instead of having to write that all out, it's already there, and we're just taking the gradient of that. And so that's all this proof is. When we do that, we're going to notice, oh, hey, I don't want to go too far. I think I did go too far. So again, taking the partial derivatives of our curls, we're going to get a lot of second partial derivatives. And with Fubini's theorem, it doesn't matter if I went with x last, with y first and x last. That's still going to cancel out if I went with x first and y. So again, you're going to find that all these are going to cancel out, and that's why we get 0. If our vector field is the velocity of a fluid or gas, then the divergence of our vector field represents the net rate of change with respect to time of the mass of fluid or gas flowing from the point xyz per unit volume. In other words, divergence on our vector field measures the tendency of fluid to diverge from a point xyz if the divergence of F equals 0. And F is said to be incompressible. So again, we're dealing with the fluid on or how it's behaving on our vector field. So if the fluid enters the neighborhood, and then if more fluid enters our neighborhood than leaves it, then divergence is said to be negative. If we have our region, and as fluid flows on our region, the same amount that enters our region, I'll try to represent this with, so say this is our region on our vector field. If more fluid as it goes into our region enters, so again, I'm going to represent that by the length of our vectors, enters, then leaves. So notice how the vectors are small. That's going to be, or that's going to have a negative divergence, all right? Because when we measure this, it's the amount that leaves. And so because less is leaving, more is filling up in this neighborhood, then it's said to be negative. So divergence would be negative when fluid is gathering in this, in this neighborhood, and less is leaving than that is entering. So that would be negative. Now, if it's the same, as fluid goes into the neighborhood, you're getting the same distance, these vectors, then that's said to be incompressible because, your divergence here would be 0 because, you're not, more or less is not leaving as entering. So, that net displacement is still going to be the same. So the divergence would be 0 and is said to be incompressible. And then what if, as you have some that comes in, but then more, as you go through the neighborhood, then more is leaving, then that's said to be, your divergence is said to be positive. More fluid is leaving than entering. All right, and then again, they're said to be incompressible when your divergence of F is equal to 0. I kind of said that, so hopefully you understand that. I might kind of go over that before class starts today too. All right. So again, the vector field F is shown in the xy plane and looks the same in all other horizontal planes. In other words, F is independent of Z and Z component is 0. So that helps us a little bit with everything. Now, I'm going to show you two ways to do this. I'm going to show you, through all the steps, and then I'm going to show you how you could just draw it out and write what we have. But our vector field is given by F, and we have the I, J, and K component. And we know that our K component, which R is going to represent Z, that's equal to 0 because its Z component is 0. Then we know that P and Q don't vary in the Z direction. So we could say that all of our partial derivatives of R with respect to X, Y, and Z are going to be 0 because R is equal to 0. And anytime we do the partial of P with respect to Z or the partial of Q with respect to Z, we also know that those are going to be equal to 0. Now, one thing that you can notice here says X is increasing. So as we're going along the X-axis, the X component of each vector increases. So the vector is getting longer the further we're going towards in the X direction. While the Y component remains constant. So again, we're not it's not increasing in the Y direction, it's just increasing in the X direction. So we know that the partial of P with respect to X is going to be greater than 0, and the partial of Q with respect to X is going to be equal to 0 because that Y, it's not changing. As we go, in the Y direction, same thing's happening. Our Y is getting, our Y component is, stretching, so that's changing, so it's getting positive. So our partial of Q with respect to Y is greater than 0, but notice that in the X direction, it's not getting, it's not going further in the X direction. So our partial of P with respect to Y is going to be equal to 0. And so when we do that, then we can just use our formulas, all right? And, using all of our values that we have here and plugging into our formulas, divergence of F is going to be positive. All right, how do we know that it's going to be positive? Because we know that here's our divergence equation, and we know that these two values here are both greater than 0, and we know that that value is 0. So we know that our divergence of F is positive. The curl of F, when I look at that, I'm just plugging into that beginning formula at the very beginning of class. And we know that when we plug these in, well, we're just going to have, oh, that's 0, that was 0, 0, 0, 0, 0. And so when we looked at everything, we noticed, oh, hey, I'm just going to be getting 0 values for all of these. And because I'm getting 0 values for all these, my curl is going to be, the curl is going to be 0. So that's one way to tell, is working through all this and finding out, all your partial derivatives, what they should be. Another point is just, okay, let's just go ahead and draw a region there. All right. Remember what divergence is. Divergence will tell me if this is going to, turn in any direction. All right. Is more... Hold on 1 second. Here, I'll go ahead and explain that in a second. But another thing that you can do here is you can go ahead and, if we, put a region in there, we could tell, okay, would it be spinning in, in a direction? Would it be spinning in the positive direction or a negative direction? And so forth. Or, if we, put our region there, is more going out than coming in, and vice versa. All right. So that about does it. I'm going to talk a little bit about the Green's theorem for, very briefly. And then after that, we are finished with notes. So, The curl and divergence operators allow us to rewrite Green's theorem in versions that will be useful, in some of our later work. So, suppose that the plane region D is boundary curve C, and the functions P and Q satisfy the hypothesis of Green's theorem. Then we consider the vector field PQ. Its line integral is, and again, since it's on a simple region, it's going to be defined by that. And then if we do the curl of this, and notice that our curl, we're still using our z component, but that's going to be taken as 0. Then the curl is just going to be given by the partial q with respect to x minus the partial p with respect to y. Okay. The curl of f with the dot product of our k component is just going to be the partial of q over the with respect to x minus the partial p with respect to y, k, and then dot k. And when we do this, the k's are going to cancel out, and we're just left with the partial of q with respect to x minus the partial p with respect to y. So then this will allow us to rewrite the equation in Green's theorem in the vector form. And so instead of saying, the partial of p dx plus q dy, we can go ahead and say, oh, well then, when we actually work on this, we can change this to the double integral of our curl f dot k dA. This equation expresses the line integral of the tangential component of f along C as the double integral of the vertical component of the curl f over the region D enclosed by C. And again, we're going to use this a little bit later, and so we'll go over it more in depth then. And this version of Green's theorem says that the line integral of the normal component of f along C is equal to the double integral of the divergence of f over the region D enclosed by C. All right, that about does it. I hope that y'all enjoyed.